Hello students, let us solve problems on continuity from the exercise 5.1 and NCERT textbook. Prove that the function fx equal to 5x minus 3 is continuous at x equal to 0, at x equal to minus 3 and x equal to 5. So here the function is 5x minus 3. So before solving the problem, we should understand the function first. So here the function is fx is 5x minus 3, and this function is defined for all real numbers, for all x belongs to R. Though it is not given to us, but we have to understand that this function is defined for the whole set of real number, since it is defined under any value of real number. So in order to prove the continuity of a function, we have learned that we must, let us state at x equal to 0 first. We have learned that in order to prove the continuity of a function at x equal to 0, we must first check at 0, the value of the function at 0, and we must check the value at a value slightly less than 0, and we must check the function at the value slightly greater than 0. So these are the 3 points at which we have to check when we have to check for x equal to 0. First at 0, and a value slightly less than 0, and a value slightly greater than 0. Now see the function. At 0, the function will be f of 0 will be 5 into 0 minus 3 will be minus 3. And at a point slightly less than 0, the function is the same. And at a point slightly greater than 0, the function is again the same. So we have learned that this is when we write x tends to 0 minus, it is at the point slightly less than 0. So the function is the same. So here x tends to 0. So what do you write? In place of x we put 0. So what we get? Minus 3. So again, the right hand limit when x is slightly greater than 0. What will be the value of the limit? When x is slightly greater than 0, also the function is the same again. So here again we put the value of x to be equal to 0, because the value of x is very close to 0. So it is 0 only. So here again it is minus 3. So at 0 it is minus 3, at a point slightly less than 0 it is minus 3, and at a point slightly greater than 0 it is minus 3. Therefore f of 0 equal to limit of x tends to 0 minus equal to, so this function is continuous at x equal to 0. Similarly, at x equal to minus 3, we do it in the same way, because here this function is defined for, this is a function which is defined for every value of real number, the same value for every point. So in this same way we will do it again. So I will not repeat the process again and again. The method is the same. So in this particular function we have to prove at particular points at 0, minus 3 and 5. So it becomes very easy. We directly take 0 and then minus 3 and then 5. So for these 2 points I will not solve it because it is the same only. Now another kind of problem, examine the following functions for continuity. Here we are not given any point. We don't have to check at any point, or we don't have to prove at any point, but examine the follow for continuity. We have to check as a whole it is continuous at every real number or not. So we have 4 questions. Out of this, if we select any one, then the other is the same. So we will do only one problem. Fx equal to modulus of x minus 5. Now we know a modulus function is defined as, for here the point will be, x will be 5. So x is, if x is greater than or equal to 5, then the function will be x minus 5, and if the value is less than 5, the function will be minus of x minus 5. or we can write this as this minus into minus, it will become plus, so 5 minus x. So this is the function, modulus function, we can write it like this. So at x greater than or equal to 5, this will be the value of the function, and at x less than 5, this will be the value of the function. So here the function is divided breaking at the point 5. So we have to check for every real number. So let us take a point, let k be a point on the real line. Then since it is breaking at, the function is breaking at 5, so if k can be equal to 5, or k may be less than 5, or k may be greater than 5. So we can have three cases: when k is less than 5, or when k equal to 5, or when k is greater than 5. So if we take the interval, first of all, less than 5 at 5, and then greater than 5. So if we cover all this, if we check for all these three cases, the whole real line will be covered. So first of one by one, the first case is when k is less than 5. So our function, what will be the value of the function when k is less than 5? For x less than 5, the function is, then f of k will be, the function is 5 minus k. So this will be the value. We don't, k is any real number on the real line. So here for every k less than 5, this will be the function. So if you take limit of x tends to, here the point is k minus fx, then if we take slightly less than k, then also it will be 5 minus x, because for every point here the function is 5 minus x. So if we put the value of k, it will be 5 minus k, and then x tends to k plus fx, limit will be, as a point slightly greater than k, also it's under this function only. So it is 5 minus x. So if we put the value of k again, 5 minus k, we see that f of k and at the point slightly less than k and at the point slightly greater than k, all the three values are the same. So for k less than 5, the function is continuous. Therefore when k is less than 5, fx is continuous. Now let us take at k equal to 5. At k equal to 5, so the value of k is exactly 5. So what is the function here? At x equal to 5, the function is x minus 5. So the function will be, f of k will be x minus 5, that is k minus 5. This will be the function. Now at the point x tends to k minus fx, that is, here it is 5, k is 5, at a point slightly less than 5, at a point slightly less than 5, the function was slightly less than 5, the function was 5 minus x, and at the point slightly greater than 5, the function was x minus 5. So for the left hand limit, that is for a point slightly less than 5, the function will be five minus x. So this is, if you put the value of k again, this will be 5 minus k, Or let us not make things complicated. Here k equal to 5, so we write it as f5. This is 5 minus 5 is 0. So again here also we write it as 5. This is 5 minus 5, which is 0. So this is the point slightly less than 5, and at the point slightly greater than 5, the function is, at the point slightly greater than 5, the function is x minus 5. So if you put the value of x to be 5, 5 minus 5 is 0. So at f of 5 it is 0. At a point slightly less than 5 it is 0. At a point slightly greater than 5 it is 0. So x equal to, at k equal to 5, the function is continuous. Now our third point, we have to check at k greater than 5. That is the third case number 3. At k greater than 5. K greater than 5. At k greater than 5, the function is x minus 5. So here at k greater than 5, f of k will be x minus 5. That means for all the values greater than 5, it will be x minus 5. For example, if it is 6, then at 6 it will be x minus 5. At a point slightly less than 6, it will be x minus 5. And at a point slightly greater than 6, it will be x minus 5. So for every k greater than 5, the function will be x minus 5. So if we take the limit, x tends to k minus f of x, the function will be the same, x minus 5. So instead of, here we have k minus 5, instead of k we write x, we write 5. Instead of x we write k, and this is the right hand limit. That means at the point when k is slightly greater than 5. This will be again the same. So when k is greater than 5, that means for all these values, if k is the representative, then if we take k, f of k will be k minus 5, and at a point slightly less than k, it will be k minus 5, and at a point slightly greater than k, it will be k minus 5. So all these 3 points are matching. So at k greater than 5, function is continuous. So for all the 3 cases we have checked, first of all, k less than 5, k equal to 5, k greater than 5. For all the 3 cases, the function is continuous.